Good afternoon, ladies and gentlemen. Welcome to this IMechE Surface Engineering webinar. My name is Liuquan Yang from the University of Leeds. We all know that the growth of the surface engineering sector in the UK is still very strong as an enabling technology, with the aim to improve the quality of the products and build a sustainable economy. Lightweight alloys and their surface treatment are very key to bring the added value to the products. On behalf of IMechE Tribology Group, it is my great pleasure to have our speaker, Professor Suman Shrestha, to be with us online today. Suman is the Vice President at Keronite and is currently a visiting professor at the University of Leeds. He has many years of experience in the PEO process across different industrial sectors. Please send me any questions you want to ask Suman using the webinar platform, and I will invite Suman to address your questions at the end of his talk. Okay, I will hand over to Suman now.
Hello London, New York, Berlin, New Delhi, Tokyo and other cities around the world. Welcome to this IMechE Surface Engineering webinar. My name is Suman Shrestha and today I'll be talking about a relatively new and advanced surface technology for light metals. This surface engineering process is called plasma electrolytic oxidation, or in short, PEO.
In today's presentation, I would like to discuss some key features this technology can address, such as reduction of process waste and manufacturing costs, and its impact on environment, extreme environmental applications, and finally, combating emissions such as greenhouse gas and particulate matters. This presentation will try to cover background on the company developing this technology and trend in surface engineering of aluminium, history of metals and surface engineering, basics and most commonly used electrolytic coating processes such as anodizing, and then move on to the emerging PEO technology. And finally, discuss some key properties of the coatings, followed by some interesting applications for thermal management and tribology in space and automotive. Keronite Limited is the industry behind this technology and specializes in the development and commercial application of an environmentally friendly and advanced surface technology throughout the world, specifically the plasma electrolytic oxidation process for light metals. Global headquartered based in the UK, Keronite serves customers worldwide using its unique and patented PEO technology. Plasma electrolytic oxidation process is sometimes also known as micro-arc oxidation or plasma anodizing. Over the last 20 years, this technology has seen widespread interest internationally, both within industry as well as in academic research. Since 2007, this technology has seen special sessions in major surface engineering international conferences and has been one of highly sought topics in industry use as well as academic research globally. The plot on the right is the Boolean search of Web of Science, which shows an increasingly growing trend in the areas of research of PEO, also known as MAO, compared to competitive processes such as hard anodizing and HV processes. This timeline of metals shows that aluminium is relatively a new invention compared to copper, bronze, and iron. Aluminium's industrial production started not until early 1900 AD, and despite this, the production of aluminium has grown exponentially over the last 100 years. Today, aluminium production is more than all non-ferrous metals combined and is considered as second king of metals after steel. Today, aluminium is used in almost every industry. We can find aluminium in our everyday life products such as watches, phones, laptops, cooking utensils, cars, to larger structures such as ships and bridges. It is now also being used in highly aggressive oil and gas environment. However, it is aerospace and space satellites that have seen a widespread use of aluminium, and more recently it has started to gain attention in high volume automotive applications such as brake discs, pistons, and suspension tubes with high corrosion and tribological performance requirements that are expected to offer major efficiency gains and impact on exhaust and non exhaust emission reductions. Aluminium is a very attractive engineering metal with excellent mechanical and physical properties. It is a much lighter alloy and is 66% lighter than steel with high strength to weight ratio and offers greater payload options and efficiency improvement. It offers easier machining and manufacturability, for example, production of wrought, extrusion, rolled, cast, powder metallurgy, and additive manufacturing forms. It is also a highly recyclable and sustainable material. Despite its highly favorable properties, some key issues such as poor corrosion and wear resistance limit its widespread use in critical applications. Aluminium is relatively a new metal compared to steel. However, its surface protection by anodizing had started already during early 20th century. Anodizing is probably the most widely used surface treatment for aluminum alloys, primarily for non-aggressive applications. However, increase in the use of aluminium in aggressive environments have us necessitated to explore newer and robust surface treatment processes. In this context, PEO can become a very viable electrolytic process, but it is not until late 20th century it has started to gain wider research interest in the former USSR. By early 2000, Keronite PEO was patented and a lab-scale setup was built in the UK with a view for its industrial exploitation. We are always in continuous search of newer technologies because of requirements to reduce weight and improve efficiency, limitations with current surface engineering methods, for example, plating, plasma nitriding, PVD, thermospraying, anodizing, and paints, requirements to coat either very large, very small, or highly complex parts manufactured by additive manufacturing, and finally, environmental legislations that demand replacing processes with environmental issues such as cadmium, hexagon chrome, acids, solvent, and heavy metals. Now, let's talk about most commonly used and competing processes for aluminum alloys, such as HVOF, hard anodizing, and plasma electrolytic oxidation. High velocity oxyfuel process has been common now in industry for depositing wear resistant coatings on steel and other substrates. But on aluminum substrate, the process is still challenging due to large CTE mismatch between the substrate and the deposited materials. It is a line-of-sight process where the coating material in the form of spherical particles are heated using the oxygen-fuel mixture to high temperature and propelled towards substrate at supersonic velocity. The nearly molten particles upon impact adhere to the substrate, and the adhesion is mostly by mechanical keying or interlocking. Now let's look into a most common electrolytic coating process for aluminium. Anodizing, as it states, the part often aluminium is made an anode, a positive terminal in the electrolytic cell. Part is immersed in an electrolyte consisting of an acid solution with its temperature tightly controlled to give the desired properties. For example, in case of hard anodizing, sulfuric acid is maintained between 0 to 5 degrees Celsius, and this results in a hard, dense, dull gray coating. Usually, a DC current is applied, and the voltage often does not exceed 50 volts, for example, in the case of hard anodizing. At anode, aluminum is oxidized to aluminum 3 plus cations, and with abundance of oxygen anions in the solution, aluminum oxide is formed on the surface of the part, while hydrogen is produced at the cathode surface, typically a stainless steel sheet. Let us now look at plasma electrolytic oxidation. In principle, it's very similar to hard anodizing in the sense it is also an electrolytic process, thus enabling to treat components with highly complex geometries with small internal bores and restricted access. However, it differs from the anodizing in terms of, firstly, PEO uses environmentally safe alkaline electrolyte, i.e., no strong acids as in hard anodizing. Secondly, it uses modulated AC voltage, thus the component swings in between being anode as well as cathode. Thirdly, it employs much higher current densities, an order of magnitude or greater, allowing voltages to exceed the layer's dielectric breakdown strength and subsequently generating plasma on the component surface. And finally, a combination of controlled high voltage energy pulses and both anodic and cathodic cycles with plasma chemical reactions leads to growth of an oxide film and its subsequent conversion from an amorphous to its crystalline form. Let me try covering some basics of the PEO process. This slide shows a schematic of an actual PEO process voltage-time relationship. The voltage in y-axis has been split into 4 stages. During stage 1 and early stage 2, these are classical anodizing steps, though in alkaline solution. Oxidation, passivation, followed by gas evolution, formation of an amorphous layer are the main steps. By late stage 2, presence of luminescence is noticed. Upon further increasing the voltage in stage 3, microscopic plasma discharges are often noticed until the beginning of stage 4. Depending upon the metal-electrolyte interactions and energy inputs on the surface, coating growth is sustained at 1 to 2 microns per minute for dense coating. By stage 4, there will be formation of powerful arcs at discrete locations on the oxide film, primarily at defects of the electric barrier where high energy density is focused. For most tribological applications, and key to a dense and hard coating, formation is to sustain the PEO process within the limits of zone 3. Further continuation in zone 4 results in extremely slow growth of the oxide thickness and results in highly porous and rough coating, largely due to these heavy arcs. Today, most research is focusing in understanding the relationship between metal, electrolyte, and electrical power density upon these discrete pulses. And for this, better understanding in power electronics, shape, and amplitude of the waveforms with controlled energy distributions at individual pulses are largely being of specific research focus. Let me show you a short video of Keronite's production setup, capable of coating multiple parts. The fundamental science behind the PEO process, as discussed in previous slide, might appear complex, and the technology often involves juggling between various aspects of engineering, including electrolyte formulations, electrical parameters, mechanical engineering, and material science. However, once the process is finalized, it can often be controlled using advanced PLC systems, and the technology is ready for digital manufacturing. In previous slide, we briefly talked about the importance of control energy input during these discharging events. By doing so, we can create porous multilayer, an extremely dense layer, or even control pore architecture within the coating, depending on the application requirement. The slide shows SEM images of the free coating surfaces and their respective cross-sections. On the left image, oxide eruptions and skeletal porosity provide high surface area for adhesion of secondary materials, for example top coats, or for lubrication. On the middle image, homogeneous coating surface with well-distributed network of microscopic pore architecture, molten solidified plugs and shrinkage cracks provide an extreme dense coating. And on the right, coating porosity, pore architecture, thickness, hardness, phase structure can be designed depending upon applications. For example, such controlled pore architecture is very useful for optical instruments requiring low reflectivity. Now, let's look into phase transformation. We talk about high energy plasma discharges, alloy melting, fusion, and recrystallization, also shown in the video, and their subsequent effect on phase transformation of the growing oxide layer. The blue line is an X-ray diffraction trace of a hard anodized coating showing an amorphous hump. The red traces are crystalline peaks, primarily alpha and gamma aluminum oxide from the PEO coating. Cross-sectional images on the right are of the hard anodized and a PEO coating on the same alloy, showing coating thickness uniformity and hardness indentations. Micro-indentation hardness measurements from these cross-sections confirmed that the resulting PEO coating has typically 3 to 5 times higher hardness than a hard anodized coating. This slide shows SEM images of the hard anodized coating and the PEO coating on aluminum alloy. These images are typical of how the coatings would appear on bends and sharp corners. While on flat regions of components, both coating would appear uniform in thickness, it is the corner that differentiate those two coating types. The left images are the surface SEM, while the right images are the cross-sections on the same regions. The hard anodized coating on corners is well known to suffer through thickness and wide-opening truncated V cracks. These defects in the hard anodized coating are of major concerns due to large fatigue drops as well as becoming regions for premature corrosion initiation sites. On the other hand, the PEO coating usually offers superior edge protection at corners and bends and offers a high degree of uniformity and protection against corrosion and subsequent minimal loss in fatigue, even for highly complex shapes. Let us look at the lower left SEM image. The PEO surface has abundance of oxide eruptions and peaks and skeletal porosity that provide high surface area for adhesion of top coats. One highly interesting feature of the PEO coating is its flexibility. The SEM image on the top left and its close-up is shown next to it. These two images show not only the coating consists of microporosity from the process microdischarges, but within these micropores there are numerous nanoscale porosity features. Such abundance of both micro and nanoscale pore architecture give the coating greater flexibility and high tolerance to mechanical and thermal stresses. Young's modulus, measured from such a coating, was reported to be almost one order of magnitude less than a similar monolithic ceramic aluminum oxide. A combination of pore scaffolds, very high hardness, and excellent adhesion gives PEO coatings greater compliance when compared to other ceramic coatings and their subsequent improved resistance to extreme wear. Another important feature of the PEO coating is its adhesion. This particular slide shows measured tensile pull adhesion values of PEO aluminum oxide versus chromic acid anodized layer. Thicker PEO coatings, typically greater than 40 microns in thickness, generally recorded tensile adhesion in excess of 80 megapascal, which can be considered very high. The lower columns are for thinner, less than 5 microns coatings, which show that PEO coatings, when thin, for example, for the use as pretreatments, can have similar adhesion values to a chromic acid anodized layer, which had been until now widely used in industry. It is the oxide eruptions and skeletal porosity that provide high surface area for adhesion of top coats, such as paints, and also work as reservoir for lubricants. This slide shows the effect of coatings on the corrosion resistance of an aluminum alloy. Image on top row shows the hard anodized layer already offers improved corrosion resistance to the aluminum alloy, but still shows issues at corners by truncated V cracks that are often responsible for fatigue and corrosion fatigue reductions. On the other hand, the PEO coating shows no sign of such corrosion issues due to its ability to offer even the sharpest edges with uniform coating coverage. The bottom left image shows how upon a scratch of the polymer layer the corrosion migrates under the powder coating, thus resulting in corrosion creep, peeling of the polymer layer, and the subsequent blistering and detachments. On the bottom right image, a thin PEO interlayer not only improves the powder coating's resistance to scratch, but also prevents corrosion creep and subsequent underfilm corrosion migration. On this slide, the graph on the left shows sliding wear resistance comparison of the various hard coatings against steel. The vertical axis is the wear resistance and the horizontal axis is the surface hardness in Vickers. The plot clearly indicates increasing sliding wear resistance of the materials with increasing surface hardness. HVOF coatings, such as tungsten carbide cobalt chrome, are considered as replacement for hard chrome plating and does offer substantial wear resistance to steel as well as aluminium. But it is the PEO coating, due to its substantially higher hardness, adhesion, and flexibility, offers much improved wear resistance than those in comparison. On the right, the column chart shows abrasive wear rates of various materials. The columns show both the steady state and over 1000 revs volumetric wear rates. Again, this plot suggests that PEO coatings can offer better wear resistance than anhydride steel, thus enabling light materials to be considered for potential replacements of heavier steels. An often sought and important property from a coated material is its fatigue life. Often, coatings in general are reported to result in fatigue debit. Most commonly used hard anodizing and aluminum alloys often reduces fatigue life by 50%. This slide shows some fatigue test data for the uncoated and PEO coated 2000 series alloy without and with effective pre-corrosion. The PEO coating does reduce the fatigue life, but not exceeding 20%. The interesting result is the effect of pre-corrosion. The uncoated alloy reduces the fatigue by almost 75% when corrosion is present. However, the coated material is seen to experience only a small reduction in the fatigue performance after corrosion. This slide shows how porosities in the PEO coating can be beneficial features, not only to offer flexibility and low stiffness, but also act as reservoirs for impregnation and retention of lubricants, thus giving the surface a composite nature, offering low friction and low wear. Hard coatings, such as nickel silicon carbide, is often crosshatch honed to retain lubricants, but these disappear fairly rapidly during wear, thus minimizing the film layer and displacing lubricants from contact zones. PEO coatings with the pore reservoirs filled with lubricants offer better retention of lubricants and subsequent surface durability. On the next slides, we will discuss some interesting projects we have been working more recently that include space and automotive applications. This slide shows a growing trend in the satellite market, predominantly micro and small sats in low Earth orbit, communication, telecom, and meteorological satellites and GPS. SpaceX, Amazon, and Google are probably leaders in these areas now. In most of these satellites, there will inevitably be use of aluminium as a preferred material for various components. Increasing interest in the use of lightweight aluminium is also driven by, firstly, the cost saving factor, and secondly, the ability to increase payload. A reduction of 1 kilogram for liftoff is estimated to save 30 to 50,000 pounds in launch costs. Coating for space is also a major business. UK engineering coatings is worth £11 billion and affects products worth £140 billion. One specific requirement that is sought for almost every space component is the thermal control properties. Good and stable thermo-optical properties are very important, especially from the beginning of life to end of life of a space vehicle. In this regard, usually black and white coatings are chosen. Black coatings with high emissivity, epsilon greater than 0.9, and high solar absorptivity, alpha greater than 0.9, is required to facilitate radiant heat transfer among internal components. On the other hand, white coatings with epsilon greater than 0.8 and low alpha less than 0.3 for direct solar radiation exposures and resistance against UV radiation, proton, electron to minimize darkening upon such exposures. Another usually sought properties include prevention from cold welding, fretting, and impact wear in space. While other properties outlined here are usually also required for successful and mission durability, key coating characteristics such as adhesion, no particle generation, resistance to cosmic rays, low CVCM, and resistance to extreme cold and hot temperature during thermal cycles are equally important. Now, let's look into thermal control and why it is so important. Firstly, low temperatures help reliability of components. Secondly, narrow temperature ranges are often required for sensitivity of detectors. And thirdly, small temperature gradients are needed for pointing of instruments and spacecrafts. As mentioned in the previous slide, key parameters of thermal control include solar absorptivity, which controls heat absorbed by external spacecraft surfaces, and infrared emissivity that controls heat radiated to space. There are different thermal control methods such as passive thermal control and active thermal control. Coatings do belong to passive thermal control method, and this approach benefits from no mechanical moving parts or fluids or no power consumption requirement. Passive thermal control approach is comparatively simple to design, implement, and test, and this has low mass and cost implications. This approach is also highly reliable. This slide shows reflectance of most widely used in space, commercial black coatings. It is important that the coatings offer predictable properties throughout the mission, and Keronite black PEO is shown to offer highly stable and favorable specular reflectance values at various wavelengths. Some examples of the black PEO coated components used in various space missions, including Earth observation and environmental mapping satellites, are shown. These coated pictures show that satellite parts made of aluminium alloys are often of highly complex shapes. The surface of the parts requires to offer various functionalities, including low reflectance black surface and minimized stray light, while giving good thermo-optical characteristics in terms of alpha and epsilon. Of specific challenges are these parts have sharp edges, complex masking requirements, thin ribs, and deep pocket features. These features present enormous challenges for most surface technologies, especially those with line of sight requirements. And for such situations, an electrolytic PEO process can offer unique solutions. We talked about black thermal control coatings. However, space components also need white coatings that have higher reflectance with low alpha, high epsilon. Historically, these coatings are organic paint-based formulations, and in some cases, ceramics, for example, zirconia or titania loaded formulations as pigments. Modern space components are required to last long during their mission in extreme temperature fluctuations, as well as high temperatures, such as the Bepi Colombo mission, where external surfaces of the materials are expected to reach 500 plus degrees Celsius. Organic paints cannot operate at such high temperatures and would disintegrate or lose its performance. White ceramic coatings that are created by PEO are inorganic in nature and are good candidates to survive high temperature applications. For the BEPI mission, components such as thermal shields are made of thin aluminum sheets. In such cases, electrolytic processes are the most appropriate ones. Keronite PEO coated 2219 thermal shields were exposed to high temperature, high UV, and high solar constants over 1800 hours of testing demonstrated stable thermo-optical properties, i.e., predictable beginning of life and end of life performances. As such, the Keronite PEO coating was selected for the Bepi Columbus flight mission. The results of this work has been published in the Journal of Spacecraft and Rockets. Another important requirement for a space component is its ability to resist failure by cold welding, which is a mechanism that leads to seizure of moving or stationary parts requiring disassembly caused by direct contact of bare metal surfaces, either by adhesion or by cohesion. Cold welding can arise from two primary forms of wear. Fretting wear. It is a process that occurs at the contact area between two surfaces under load and subject to relative motion by vibration or some other forces, leading to excessive wear and debris formation. And impact wear, a process that occurs at the contact area between two surfaces under repetitive load, resulting in elastic and plastic deformation of materials, crack initiation, and debris formation. Often, space hardware are subject to several thousands of opening and closing, resulting in small oscillations at contact surfaces, for example, space antennas. This results in degradation of surfaces, including natural oxides and coatings, resulting in cold welding. An example is shown on the right. Vibrations of Galileo spacecraft high-gain antenna during ground transport and launch caused destruction of protective layers on hold-on points by fretting. This resulted in cold welding, failing deployment of the antenna. Now, let's look into how the cold welding mechanism occurs. In earth and air, under repetitive contacts, fretting or impacts, destructions of natural oxide layer results in lubrication, debris formation, or excessive wear. In space or vacuum conditions, under the same repetitive contacts, the oxide layer does not heal, and as a result, two metals bond together, causing unwanted seizure by sticking. The use of a hard and durable coating can solve various problems, including minimizing wear, debris formation, or sticking by cold welding. Let us look into the fretting and impact wear behavior of various coatings on the slide. While high adhesion between the coating and the substrate is always required, adhesion between two surfaces in contact is often desirable, and thus, lower the adhesion value in these bar plots, better the combinations are. So if you look at aluminum to aluminum adhesion, it is extremely high during fretting and impact tests, whereas with appropriate coating systems, adhesion values during both fretting and impact tests are considerably lower. PEO-coated aluminum substrate against widely used steel counterpart material shows considerable performance enhancement with low adhesion values during both fretting and impact loading conditions. Surface SEM on the top image shows considerable coating damage to the anodized layer during fretting tests, whereas the PEO coating on the bottom sustained no damage to the surface except for some material transfer from the steel counterpart. This coating has now been approved by Max Planck Institute and has been used on the JUICE mission. One of the benefits of the PEO coating is its ability to retain solid lubricants, such as molybdenum disulfide, in its pore architecture, thus giving a durable, low-friction composite structure, especially when protection is required against high contact stress, low debris under fretting and sliding wear scenarios, and in vacuum conditions. Some test results with Keronite PEO composite coating used on an aluminum alloy show extremely low friction coefficient values during high contact pressure tests in a cryogenic environment. These parts are currently used on the EMIR GRISM cryostat wheel bearing on one of the world's largest space observatory. The next few slides we will talk about the potential use of hard PEO ceramic coating on aluminum alloy for automotive braking applications. Heavy cast iron discs are part of what is known as the unsprung mass, which amplifies the effect weight has on fuel efficiency or battery efficiency and range in the case of electric vehicles. Furthermore, iron brake wear particle matters in urban air pollution has been linked to a range of acute health conditions. For these reasons, iron brakes are a barrier to making better inroads into the wider challenges of PM and GHG emissions. Various attempts have been made in relation to the introduction of lighter, lower wear solutions such as aluminium metal matrix composite, carbon fiber reinforced ceramic, aluminium brake disc combined with brazed aluminum oxide, hybrid aluminum hub iron brake surface with HVO coating. All above listed options have limited success, either due to very high costs such as MMC or CFRC, or technical challenges such as cracking of the ceramic plates in the case of brazed alumina, or galvanic corrosion issues with the HVF coating. Considering the above challenges, aluminum alloy combined with a hard-wearing ceramic coating can be a potential solution. For this reason, we started to investigate the PEO-coated aluminum brake rotor, and this is what we will be learning on the next few slides. An important characteristic of a braking system is its friction behavior. So we started our initial research on PEO-coated aluminum rotor with the University of Leeds using a small-scale bench dynamometer. The graph on the right shows comparative friction data at various contact pressures for the PEO alumina, HVOF alumina, and grey cast iron as a benchmark. COF values for both PEO and HVOF coatings are rather similar and stable, circa 0.3 to 0.33 against a non-asbestos organic friction material, indicates the potential of PEO ceramic coating for the brake disc application. Follow-on research at the University of Leeds was undertaken with Professor David Barton's team. Dr. Abdul Wahab Al Naki, during his PhD, did finite elements modeling on the PEO-coated brake rotor and indicated that the PEO-coated aluminum rotor may be potentially suitable up to 450 degrees Celsius operating temperature and 1400 kilogram vehicle mass, which could potentially cover most small-sized cars from Nissan Micra to Audi A3. Brake dynamometer tests at the university showed no damage and wear to the PEO-coated rotor up to 500 degrees Celsius. While the previous research at the university primarily focused on bench dynamometer tests, this Innovate UK funded 2-year project is conducting tests on aluminum alloy brake disc for the rear axle of a high-performance sports car. Aluminium disc coated with a Keronite PEO ceramic layer was subjected to full-scale AK master dynamometer tests at Alcorn's facility at increasing levels of initial braking temperature. A standard low-mid brake pad was used for this current research. Details of the AK master tests are shown in the table that comprised various test sessions in each test block, such as mu green, bedding, speed pressure variations, characteristics values, and motorway snubs. Friction values are rather similar for both iron disc and the coated aluminum disc, typically 0.3 to 0.35, and is similar to the values recorded at the university tests on benchtop dynamometers. However, it is noteworthy that COF values are more stable, i.e., with less scatter for the PEO coated aluminium disc, especially during the bedding cycle. Post-AK master test results are shown in this slide. The left plot shows pad wear values at various break temperatures up to 400 degrees Celsius. Iron disc measurements were taken only after 400 degrees C IBT. Pad wear against the PEO coated aluminum disc remains almost similar at 200 and 300 degrees Celsius temperatures, but there was a sudden increase at 400 degrees C at almost twice the wear. What is interesting here is for the same 400 degrees C IBT, the pad wear against an iron disc is almost twice that of a PEO coating aluminum disc. The right graph shows the disc wear and the disc runout at 400 degrees C. Disc wear was higher for the PEO coated disc but still retained two-thirds of the coating thickness. However, disc runout was substantially lower for the PEO coated disc in comparison to the iron disc. In summarizing the aluminum brake disc coating, I've broken down the project into current and future status. In the current status, bench dynamometer test with small-scale rotors has demonstrated PEO alumina on aluminum disc has good thermal and friction performance. Final element analysis suggests PEO-coated aluminum disc may be suitable for cars up to 1400 kg. While full-size high-performance car brake disc test has indicated PEO-coated aluminum disc is suitable in terms of acceptable COF, minimal disc and pad wear, and low disc runout up to 300 degrees Celsius IBT. However, 400 degrees C IBT test may be too aggressive in the current situation, considering the large CT mismatch. Now let's look into further research in progress. Key points to consider. For use above 300 degrees C IBT, other approaches including smart braking, engine management, disc and pad materials optimization need consideration. Thermal management of aluminum brake discs may be achieved via high emissivity PA coating, heat dissipation by conduction via harbor shaft, forced convection via rotor vanes, or disc design and optimization of rubbing surface. And finally, wheel configuration, for example, alloy wheel with minimal hub, should also be considered for further research. Another interesting area for the PEO technology is about thermal swing effect and how this may help improve vehicle fuel efficiency. One recent project we investigated was high potential, funded by Innovate UK. Heat loss during the combustion stroke in diesel engine is highest due to large difference in temperature between the gas and wall temperatures. Insulating piston crown and the other parts of the combustion chamber helps enhance thermal efficiency and fuel economy. Thermal swing insulation is different to a traditional thermal barrier coating, as it has not only a low thermal conductivity lambda, but also low specific heat capacity CV, which allows the surface temperature to rise during the combustion period and decreases during the exhaust and intake strokes, reducing heat loss and prevents intake air heating. A good thermal swing coating combines low thermal conductivity and low volumetric heat capacity. Let's look into this graph. On y-axis, we have thermal conductivity, often expressed as lambda, with units watts per meter per Kelvin. Low lambda reduces heat transfer across the coating thickness to the piston. On the x-axis, we have volumetric heat capacity, CV, in kilojoules per meter cube per Kelvin. Low CV reduces heat uptake and allows release during the exhaust, intake, and compression strokes. Air has one of the lowest lambda and CV values, while mullite and aluminosilicate groups have relatively low thermal conductivity and low CV. So the aim of this research is to come up with a ceramic coating by leveraging the PEO process capability to create a mullite aluminosilicate group with high volume fraction closed pores and resistance to very high heat and thermal cycles. One commercial coating claimed to have such characteristics is known as SERPA, i.e., silicon reinforced porous anodized coating, shown by the star symbol on the graph, which was developed by Toyota. On this slide, the top left is a porous hard anodized coating used as a benchmark coating. And at Keronite, we attempted to leverage the coating properties and process versatility to enhance the thermal characteristics, for example, by creating a more porous architecture. The SEM image on the bottom right is one of the Keronite PEO coating, where we have managed to create a much higher pore density, comprising both microscale and nanoscale features by varying process parameters such as electrolyte and PEO electrical regimes. The graph on the right shows thermal conductivity lambda values of the coated alloy at test temperatures ranging from 100 to 250 degrees Celsius during the hot plate test method. Keronite PEO coating was shown to have lower lambda values than a porous, hard anodized coating, believed due to the mullite layer with high pore density and acidia. Now, let us revisit the previous lambda versus CV graph we just discussed and superimpose the PEO data. The graphs show results from two different experimental approaches, the first being the hot plate method and the second one being from the laser flash approach. What is interesting here is that the two standard approaches give different lambda and CV values for each material. Usually, hot plate method resulted in consistently lower lambda values, while the laser flash technique gave higher numbers. However, CV values were rather similar in both approaches. The key message is that in both approaches, one PEO coating variant demonstrated rather similar or even lower lambda and CV values when compared to a benchmark porous hard anodized coating. Based on encouraging high potential results, we moved on to the next project Atlas, i.e. Advanced Thermal Layers for Automotive Systems. This project was also funded by Innovate UK IDP 13 under Low Carbon Vehicle Systems Integrated Delivery Program. Key partners in the project included Keronite, JLR, TWI, Tata Technologies, and the University of Nottingham. This program considered developed thermal coatings for Ford Puma diesel pistons, single-cylinder engine tests at Nottingham University to measure fuel economy and emissions, and finally, simulation and modeling to predict impact on vehicle range and economy. Gross thermal efficiencies of the two PEO coating variants are shown in the graph, and comparisons have been made with uncoated piston as a baseline material and with an anodized piston. The plots show that anodized piston was even slightly worse than the baseline alloy. However, PEO coatings show some improvements in efficiency gains. One PEO coating type, PEO1, demonstrated the best performance with more than 3% gain in the fuel useful energy and an equivalent improvement in the indicated thermal efficiency. A detailed work has been submitted for publication to the Journal of Applied Energy. Summarizing PEO for piston crown. Thermal swing coatings represent an exciting opportunity to achieve meaningful increases in ICE efficiency. A good thermal swing coating combines low thermal conductivity, low heat capacity, and low density. Analysis by Keronite and our partners has given good confidence that PEO coatings can at least match the current benchmark coating on these metrics. Under idealized part load conditions tested, Keronite PEO coatings demonstrated the best performance with more than 3% gain in the fuel useful energy and an equivalent improvement in the thermal efficiency. Summarizing the PEO characteristics. Advanced PEO coating can offer life extension of 2 to 10 times compared to a hard anodized coating because of its extreme hardness, wear resistance, fatigue endurance, and very strong adhesion. It can replace processes with environmental concerns. It is an enabling technology that can help replace steel on various highly demanding applications. It is compatible with novel manufacturing processes such as additive manufacturing and powder metallurgy. And finally, this slide shows an attempt to create a simple traffic light process selection approach for three most widely used coating technologies that can be applied to aluminium. While hard anodizing has been a popular choice, but its use of strong acids in the process has been of issues due to environmental concerns. Also, increasing application demands in terms of extreme corrosion, wear, and other functional requirements necessitate more advanced surface technologies. While hard anodizing would offer some level of corrosion and wear protection, for enhanced multifunctional requirements, one would require to choose new technologies such as HVOF or PEO. Perhaps this slide may be used as starting guidelines for process selection depending upon the use of aluminium alloy with respect to its application needs. Thank you all for listening to the talk today. I hope that you have found some information in this presentation useful, in particular, applications with the use of aluminum alloys in combination with environmentally friendly PEO surface technology. I would also like to thank a number of organizations listed in this slide for allowing me to use their results from our collaborative research projects and also for their funding. Thank you once again.